So, now we will be continuing with our discussion on BIST. So, in our last lecture, if you recall, we were talking about pseudo random pattern generation and how we can use LFSR to generate the patterns for built-in self test of a circuit. Now, we have also said that LFSR test patterns are very cheap and inexpensive in the sense that the hardware required for the test generation is very simple. They can run at the maximum rated clock frequency of the chip, so that you can apply the clock frequency at the rated you can apply the patterns at the rated clock frequency. So, which can also help in detecting many delay related faults. Okay. So, today we continue our discussion and look at the remaining part of the BIST architecture. We have so far seen that how a circuit under test can be excited with pseudo random patterns from a linear feedback shift register. But suppose I have a circuit with 100 inputs and I am applying, let us say, 1 million or 1 billion patterns. So, I will be having 1 billion sets of output responses. What do I do with those? Okay, or 1 million such set. So, we really cannot afford to store all the responses in a ROM, some kind of memory, and compare them vector by vector. It will be too expensive, right? So, what is done is that using some method we have to reduce the size of these test responses to a small and manageable volume before you can actually compare with the corresponding fault free value, right. So, that is the objective here. So, we talk about something called test response compaction. Now, we shall see a little later how compaction is different from compression. Compaction and compression are not the same thing. So, I have just now said that the circuit under test, when you are applying the test data, the responses can generate huge volumes of data. Like one example, 5 million patterns are applied, there are 200 outputs. So, you are landing into 1 billion bits of response. So, you really cannot store so many bits in a ROM on chip and compare during testing, right. So, it is absolutely mandatory to do some kind of a compaction to reduce this billion bits. Well, now you may ask that, well, I have to start with this 1 billion bits. Well, I have to compact, I agree, but compact to how much? Should it be 1 billion to 1 million, 10,000, 1,000, what will be a good number? But we shall see using some theoretical justification that practically compaction is done in such a way that the final value that is generated is just a 32-bit or a 64-bit number. So, from 1 billion we come down to just 32 bits or 64 bits. So, it is a huge compaction. Okay? This we will see. So, there is one issue that arises here. So, we are doing compaction. Okay? So, compaction means what? We are doing some kind of a many to one mapping, like we are mapping a large set into a small set. Let us say this is the set of all possible responses. And this is the set of compacted information. So, in the example that I have just now mentioned, I said that we are possibly compacting 1 billion bits of data into, let us say, 32 or 64 bits of data. It is a huge compaction. Now, what I do, I find out that for my circuit without any fault, what should be my good compacted information, that I say this is my golden signature. this is my golden signature. So, after my test experiment is done, I compare my compacted information against my golden signature. But the problem here is, because I am doing a very kind of heavy kind of a many to one mapping, 10 to the power 9 things are getting mapped into 64 things. So, even many possible responses might get mapped into the same golden signature. So, some errors might get mapped into the golden signature, and those faults will go, they will go undetected. Yes, we accept that, because we are doing compaction, some faults will go undetected, but what is the probability of that, we shall evaluate that later on. Okay. So, this is what we are saying, the golden signature is stored on chip, many to one mapping, some of the faults might go undetected. So, we will have to look at it, that what is the probability for that. Okay. So, we first look at some relevant definitions. This aliasing is something we are just now talking about. This aliasing is the phenomena where the signature in the presence of a fault matches with the golden signature, and therefore, the fault goes undetected. So, I have a circuit, I apply those 1 billion patterns, I get the 64-bit signature, I compare it with my good signature, I say that there is a match, but it may so happen that there was some fault in the circuit, but somehow the final signature remained the same, because it is a many to one mapping. Okay. Okay. Now, let us differentiate between compaction and compression. Compaction is a mechanism which drastically reduces the number of bits, like we mentioned 10 to the power 9 to 32 or 64. This results in loss of information quite obviously, because from this 32 bits we cannot go back and recover these 10 to the power 9 original responses. Okay. This is a one-way mapping. But in compression, which we normally use in our computers, we do zip, we do rar to compress our files, that is a reversible process. We do compression, we can again do an uncompression to get back to our original. Okay. So, compression also reduces number of bits, but not this drastically, but there is no information loss, we can reverse the process. There is a process of compression, there is a process of decompression or uncompression. Okay. Now, when I talk about response compaction, and here again we are using LFSR. So, two broad approaches are possible. One where we compact a single serial bit stream into a compactor, this is called signature analysis, and the hardware is called signature analyzer. And as an alternative, several serial bit streams can be compacted, that is called multi input signature register. Like I am just showing you schematically. Like suppose you have a circuit, there are multiple inputs, but a single output, let us say. So, what I can do at the input side, I can use an LFSR to generate some random patterns and feed it here, and on the output side, okay, here again I use a special kind of LFSR which will accept serial data from here, and it will do the compaction here. But if I have a circuit like this, where let us say there are multiple inputs and also multiple outputs. So, here I can use an LFSR, and here I can use one such LFSR with every output, but that will be an expensive solution. But rather what I use a special kind of an LFSR which can take multiple inputs, multiple input signature register. So, I compact multiple output data simultaneously. Okay. This is what is the main difference here. So, let us first look at the LFSR based signature analyzer which can compact a single bit stream. So, the process is exactly similar to cyclic redundancy code generator which is used for error detection in many applications. Mathematically, what we do here is that basically we are dividing a polynomial by another polynomial and take the remainder. Now, you see any bit pattern, let us say I write a bit pattern 101101. Now, bit pattern can also be represented as a polynomial like this, that every bit position can be regarded as the coefficient of a polynomial x to the power 0, x to the power 1, x to the power 2, x to the power 3, x to the power 4 and x to the power 5. So, this bit pattern we can express as a polynomial, just take the ones, x to the power 5 plus x to the power 3 plus x square plus 1. Okay. So, any binary bit string can be represented as a polynomial. So, here we are saying is that the process is essentially one of dividing a polynomial by another polynomial and take the remainder. That will be the cyclic redundancy code, and in this case our signature. So, we treat the data bits that are coming out of the outputs of the circuit as a decreasing order coefficient polynomial, just as I had mentioned, that any bit stream can be regarded as a polynomial. So, essentially what this method does, so I have an input polynomial which is the output bit stream which the circuit generates. We divide it by the characteristic polynomial of the LFSR, and after all the bit patterns are fed, whatever remains in the LFSR, that is the signature, that is the remainder after division, and that remainder we are calling as the signature. So, we are finally comparing that remainder with the good remainder in presence of, means in the absence of faults for the good circuit. So, the good machine signature must be computed a priori and stored in a ROM, so that after this experiment we can compare, right. So, let us take an example here. So, we have a 5-bit LFSR as shown here. So, characteristic polynomial, if you look at the coefficients here, so it will be like this 1 x, x cube and x 5, and the input bit stream, let us suppose bits are coming like this. So, input polynomial, if you look at it 0, 1, 2, 3, 4, 5, 6, it will be x to the power 7 plus x to the power 3 plus x to the power 1. So, input polynomial can be regarded as x 7 x cube plus x. So, we have to divide this polynomial by this polynomial, and these are the outputs of the LFSR, let us say, but here we do not need the outputs really, because here we are doing some kind of compaction. So, we are dividing fx by px and take the remainder. So, if you do it by hand modulo 2 division, you can check that the remainder is coming as x cube plus x square plus 1. Let us see that whether this hardware also generates the same thing. So, we load it to the initial seed like this. So, we simulate the process of division step by step. We load, the point to note is that initially we load it to the all 0 pattern, all 0. Then we apply this sequence of bits 1 0 0 1 to the LFSR, and depending on the feedback, some of the bits will get modified accordingly. So, I suggest that you can work this out and see whether these patterns are matching. So, after all the bit patterns have been applied, the data that remains in the shift register is 1 0 1 1 0. These bits correspond to the input polynomial x 7 plus x 3 plus x 1, and the remainder that is coming, that is x 3 plus x 2 plus x 1, which is supposed to be the remainder. So, what we have shown through this simple example is that this special kind of LFSR structure can really divide a polynomial by another polynomial and compute the remainder. This concept is used in CRC code generation, and in the present context we are using it for signature generation. So, for detecting whether any fault has taken place or not. Okay, fine. Now comes the important part. So, what is the probability that a fault has occurred, but we are not able to detect it because it has matched to the correct signature. So, let us make a simple calculation based on some assumptions. So, we assume that m is the number of bits that you are compressing or compacting and n is the LFSR length. So, obviously, m will be large as compared to n, so the m is much larger. Okay. So, we are actually we are doing something like this. We have an m bit stream, this is coming from the output of your circuit, you are mapping it to an n bit stream in the LFSR. So, as I said, m is much greater as compared to n. Now, what means if I talk about m bit stream, we regard it like this: because of some error or fault in the circuit, this m bit stream will become something different. So, what are the possible m bit streams? There are 2 to the power m possible m bit streams. Similarly, there are 2 to the power n possible n bit streams, and out of them 1 is the good stream. Similarly, here 1 is the good signature. This is what we are telling in this slide. So, we are saying number of possible input combinations 2 to the power m, possible signature 2 to the power m. Out of this, 1 is good and one of these signature is the good signature or the golden signature. Now, we make an assumption that this input 2 to the power m patterns are uniformly distributed among the signatures. So, there are 2 to the power m patterns which are mapping into 2 to the power n. So, for any particular signature, how many patterns will be mapping? 2 to the power m divided by 2 to the power n or 2 to the power m minus n. So, these many patterns will also be mapping into the golden signature. Okay. So, we define the probability of aliasing as the ratio of the number of faulty bit streams that map to the golden signature. That means, the faults that are going undetected to the total number of faulty signatures. Now, I said there are 2 to the power m minus n patterns which are mapping into a signature, also the golden signature. Out of them 1 is good. So, number of faulty signature will be this minus 1 that map into the golden signature. Similarly, 2 to the power m is the total input bit streams, out of them 1 is good. So, 2 to the power m minus 1 will be faulty. So, probability of aliasing will be this divided by this. Now, because m is much greater than n, this approximates to 2 to the power minus n, which is independent of m. Just you can check 2 to the power m minus n divided by 2 to the power m minus 1. So, we are saying m is much greater than n. So, you can approximate this as 2 to the power m minus n. You can ignore this 1 divided by 2 to the power m. This is 2 to the power minus n. So, let us take an example of 32 bit LFSR. If n is 32, so here how much is 2 to the power minus n? 2.3 into 10 to the power minus 10. So, this is the probability with which some fault may occur, but it will go undetected. But 10 to the power minus 10 is really a very small number. If we use a 64 bit signature, 2 to the power minus 64 will be even much smaller. So, these numbers give us a confidence that even if there is a chance of some fault getting undetected, the probability is very, very low, and this method is pretty good and acceptable, right. This is the basic idea. So, multi input signature register is just an extension of this concept, because the method that we have discussed is able to compress only a single bit stream. So, if there are multiple bit stream, multiple outputs, you need one such LFSR for every output. So, you go for something called multiple input signature register, which is called MISR in short, MISR. Here we compact all the outputs into one LFSR together. There are some properties. So, means if you compact each of the individual inputs separately, compute the signature and take the XOR of the final, you will be getting the final result at the end. So, this can be proved because this LFSR feedback is linear, it obeys superposition principle, and superposition principle says that if you apply one input at a time and see the response, and if you apply all of them together, if you take the sum, it will be the same response. So, this happens, and MISR looks like this. So, MISR is a modified version of a type 2 LFSR, you can see, where you have put an XOR gate between every pair of flip flops, but depending on the characteristic polynomial, I can use this feedback point to some of the XOR gates only. Okay. Maybe I put it here, here and here, but these two there is no connection. But on the other side, we have added one additional input of these XOR gates. When I have a circuit under test, I am applying some patterns. There can be multiple outputs which are generated simultaneously. I feed them simultaneously on these lines, and this is how compaction takes place, right. So, to summarize, we looked at the various technologies, some of the technologies at least, there are some others also. The preferred BIST method we have seen, that LFSR based pattern generation and MISR based compaction. There are overheads, of course. You need the pattern generator, response compactor, control circuits, comparator, etc. But the advantages of BIST are also quite high, so that in many applications, many chip designs, you may prefer to go for BIST because it gives you much higher convenience. Reduction in test cost, obviously, you can do testing and diagnosis on field, and most importantly at speed testing. You can test at the clock frequency of the circuit. Okay. So, with this we come to the end of this series of lectures on testing. Thank you.